Good morning, everyone. It's a pleasure to be with you. Yeah, it's fine. Do you hear me? Is this microphone working? Okay, thank you. So I've been asked to talk a little bit about what is the status of knowledge about climate change after the IPCC reports, or the first contribution to the IPCC report published this summer. And I may have too many slides, so I will start with a summary slide, which shows what the situation is in 10 words. It's real. I think everybody now is aware that global warming is happening. It's us. It's very clearly the result, at least since the middle of the 20th century, from the burning of fossil fuel and also from deforestation. Experts agree, and the IPCC, of course, very much contributed to build the scientific consensus and to make it known about the human origin of the present warming we are seeing. It's bad because the impacts are serious and affect people, and of course in this workshop I should add, and I didn't write this slide, it's not only people but it's also ecosystems, of course. And the last two words are probably the most important. There is hope, because we have not only the technology but also the knowledge to avoid at least the worst climate impacts. So I see you are not yet sleeping, even though I'm not an economist, so I'm not so much going to talk about the economical aspect and maybe a little more about what comes upstream and what is threatening the existence of some species. So let's spend a second to look at this beautiful picture showing the atmosphere. It's a very thin layer of gas which protects us from a number of threats. It's very thin. It's still, we're using this thin layer as a free, and free is for you, the economist, free dustbin. It's essentially free. I mean, there's a small price in some locations, as we just heard, but it's very small yet. A free dustbin for greenhouse gases. And what we're doing by doing that is actually thickening the thermal insulation layer that those greenhouse gas constitute. The greenhouse gas let the solar radiation in, they trap the infrared radiation, radiation emitted by the surface of the planet, and this comparison with the thickening insulation layer, which I'll show you here in this animation, showing the evolution of CO2, the CO2 concentrations in parts per million. It's a proportion in the atmosphere since 1850, and you have here the temperature. And I like this presentation. You have the months of the year around the circle here, because it suggests visually what's happening, the thickening of that insulation layer around the planet. And if you really memorize this, you will understand, without any complicated climate model, any complete understanding of the carbon cycle, which I will still try to explain a little bit in a minute, why we need, as quickly as possible, if we want to avoid, since one is the cause of the other, as we know today, if you want to avoid going above a warming of 1.5 degrees C warming, which is this thin red circle here, we need to stop this thickening as soon as possible, and that means going to net zero emissions, not emitting more than what ecosystems and the ocean can absorb. Another view at this evolution of the CO2 concentration in the atmosphere is this one, showing the evolution over the last 10,000 years. So for 9,800 years approximately, it was stable. That's the entire period where agriculture was set up and many civilizations were built, etc. And then over the last 200 years, when the fossil fuel era started, you see how it increased exponentially. So this is really this increase is really the result of the burning of fossil fuel, coal, oil and gas, and also of deforestation. Why is this? This is the simple version. It's because the CO2 level in the atmosphere is represented by the water level in a bathtub. This is just because we put in this bathtub more water, more CO2, than what can be evacuated. And as long as one is larger than the other one, the level will increase. It at some point cross the threshold we don't want to cross. So now maybe a few seconds on the details. Before the disturbance of the carbon cycle by the human activities, this is how things were looking. You see two big loops of carbon or CO2 between soils and the vegetation and the atmosphere. You have numbers saying gigatons of carbon per year. You see a flux up, a flux down. They're almost balanced. It's the same for the ocean. Flux up, flux down. The total actually of the fluxes up and the fluxes down are perfectly balanced before we intervened. And if you looked at the situation at the end of the 20th century, it doesn't matter. I'm sure that Corinne Le Quéré, at the end of the day, who is really one of the top specialists in the world of this, will give you updated numbers. But just to explain, it doesn't matter. What we're doing is emitting, mostly through the burning of fossil fuel and also from deforestation, about 8 gigatons. We were emitting at the end of the 20th century 8 gigatons of carbon. You multiply that by 3.7 if you want to have that in gigaton of CO2. And about half, a small half of that, is added every year to the atmosphere. And it's only one half, or a small half, because the other half is absorbed in part by vegetation, which grows faster, and in part by the ocean. This carbon cycle is actually very well understood. This is a paper published in Science in 1975, which contained a forecast of the concentration in 2010, assuming that the trend in fossil fuel consumption then would be extended. And as you can see, it forecast a concentration of 403 parts per million, very close to what was observed. We are now at 415, but we're a little further than 2010. And it forecast a global temperature increase of 1.1 degrees C above pre-industrial, which is exactly where we are at today. So you see the understanding of many scientific aspects of climate change have been there for a long time, in particular the understanding of the carbon cycle. By the way, the effect of COVID, because that's a question often asked, is negligible. You see here again, these are parts per million in CO2. You see the annual cycle, the trend, and the effect of the COVID lockdowns, etc., the slowdown of the economy, is the difference between those two lines here. It's negligible, and that's because we are really facing an accumulation, a pollution, a stock pollution, which accumulates in the atmosphere. So if you just decrease a little bit the emissions for a year or two, it doesn't make much difference to the trend, which is the increasing level. So one word about the context in which the IPCC is doing its work. You know that there is a lot of activity related to climate confusion. I prefer to use that word than climate skepticism, because skepticism is at the root of science. And just in the US, again, for you economists, a number with dollars, it's $1 billion per year, which at least for that period for which it's a peer-reviewed paper, it's not a Greenpeace report, it's a peer-reviewed paper published in Climatic Change, which is spent every year to sow disinformation about climate change. Okay, so this is the context in which the IPCC was created 30 years ago to provide the best assessment of climate science and of knowledge about all dimensions, including economic dimensions of climate change, its impacts, and also options for either adaptation or mitigation. Is there a problem? So let me report about the IPCC Working Group 1 report. The IPCC is divided basically in 3 working groups. Working Group 1 deals with climate science, the natural science aspects. The Working Group 2 deals with impacts and adaptation and vulnerability. Working Group 3 deals with mitigation. Working Group 1 published its contribution this summer. Working Group 2 will publish its contribution in February 2022, and Working Group 3 in March. Then there'll be a synthesis report in September next year. So what does it say? It's certain that emissions resulting from human activities are substantially increasing the concentration of greenhouse gases. It calculated with confidence that under a business as usual scenario, the temperature will increase by about 3 degrees C by 2100, with an uncertainty range between 2 and 5 degrees C above pre-industrial, and sea level would increase by 60 centimeter with an uncertain range between 30 centimeter and 1 meter. With an increase in the mean temperature, there would be episodes of high temperature becoming more frequent. Some species would be unable to adapt fast enough and will become extinct, which is of course related to biodiversity. And long-lived gases such as CO2, N2O, and CFCs would require immediate reduction in emissions from human activities of over 60% to stabilize their concentration at today's level. Mark, where is Mark? I'm really sorry, Mark. I prepared these slides in a hurry last night, and I'm really sorry because I misled you. I mean, these were slides from these were slides from the quotations from the first IPCC report. I have to apologize. The point is, of course, that basically all the relevant information was there 30 years ago already, because the numbers are not that different, as I will show now, because this is the report from this summer. A very solid report, more than 200 authors, 14,000 scientific publications assessed, almost 80,000 comments taken on board. And here are some of the key aspects from that report. Now, I'm not misleading you anymore. This is really from the last summer's report. So this is the evolution of temperature over the last 2,000 years, and you see how striking the change over the last 100 years or so is compared to what happened before. This is a slide. This picture comes from the report this summer, and you see here I've added the vertical lines which corresponds to the different assessment reports from the IPCC. The one published in 1990, which I just quoted, until the last, which is on the extreme right here. And what it shows is 2 different attempts to reproduce the observed temperature increase, which is the black line there, with 2 sets of simulations. One, simulations forced with only natural factors, basically solar activity and volcanic eruptions. And as you can see, after 1950 or so, these simulations are able to reproduce some fluctuations, but not the trend. It's only the other set of simulation which became increasingly different from this one, with simulations forced by natural factors and human factors, which is able to reproduce much better the evolution. And this is why over time, and you see here the very clear evolution of the statements by IPCC about the solidity of the link between human activity and the warming, and this summer's conclusion was it's unequivocal that human influence has warmed the atmosphere, ocean and land over the last 70 years at least. It's not only the average which is changing, it's a number of other elements. The CO2 concentration is now the highest in at least the last 2 million years. The sea level is increasing at rates that are the highest over the last 3,000 years at least. The Arctic sea ice area has reached its lowest level in at least 1,000 years. And the glacial retreat, which you can see in Chamonix, not very far from here, is unprecedented in at least the last 2,000 years. It's a number of extreme events which change either in frequency or intensity. The two categories for which things are the clearest are the extreme heat event, heat waves, etc., with a lot of consequences for health and for ecosystems, and heavy rainfall, leading very often to floods, as we have seen this summer in my country, Belgium, and many other parts of the world. Why are heat waves increasing? I don't think it requires long explanation. If the average is moving, of course, the probability of being above a threshold increases significantly, and this can have terrible consequences. The summer of 2003, it was 70,000 deaths in Europe in a few days. The other category of extreme events, heavy precipitation, may be a little less intuitive. The reason for the increase in intensity, I mean, the main reason, it's not the only reason, but the main reason is this one. It's a basic physics law of Clausius-Clapeyron, which says that that warmer air leads to more evaporation and a higher water content. Each degree Celsius leads to 7% more water vapor in the atmosphere, which means that when the conditions are met for that water vapor to condense, the quantity is higher in a given time, and that can lead to floods. Now, looking at the future, we have to work, of course, with scenarios. These are the 5 key scenarios, SSP something 8.5 for the top scenario to SSP 1.9 for the lowest scenario. You see how they shape. It looks like, as far as the CO2 emissions are concerned, either a kind of business as usual trend or a strong decrease for the lowest scenario. And if you feed those scenarios to climate models, this is what you get in terms of global temperature. You see that, after all, it's not so different from what I quoted from the first report in 1990, a range between 1.5 and approximately 5 degrees C by the end of the century, with a stabilization in this case and an increase, a continuing increase then. Of course, it's spread in space. Land heats faster. The Arctic heats significantly more than the rest as well. Increases, which are shown by the number of dots here, for different warming levels in the frequency of either 10-year heat wave, 10-year typical heat wave, or 50-year event, with, for example, in a plus 4 degrees C warming, a probability that increases by almost 40 of having events that have a 50-year frequency in the unperturbed climates. If you look at the health effects of that increase in wheat, I'd like to draw the attention. This is not coming directly from the IPCC report, comes from an article, but I'm sure it will be covered in the Working Group 2 report. And that is that the combined effect of heat and humidity in tropical regions, for example in India, can be killing much more than what has been understood before. If you go above 35 degrees C and 100% humidity, you are killed in 6 hours approximately. It's impossible to stay outside by that temperature. And you see that for this temperature, for this scenario, some parts of India would be quite close from that situation. There would be changes in precipitation patterns as well, with broadly an increase in the world because more evaporation, but also parts becoming drier, for example, the Mediterranean basin. There's an increase in the intensity of heavy precipitation, as I mentioned earlier. The increase is not as strong as the increase for heat waves, but still it's there. In the long term, there's also a big concern about the evolution of the ice sheets in Greenland and Antarctica. Right now, the Antarctica, just to give that example, delivers every day and a half this volume of additional water, which is Central Park in New York, over the volume with the top skyscraper. Every day and a half, it's 1 billion cubic meter added to the ocean. And this results, together with the other 2 factors influencing sea level, water expansion and the melting of glaciers, which I mentioned earlier, to these projections for sea level between 50 centimeters and 1 meter by the end of the century. Again, not so different from the numbers in the 1990 report, but with a novelty in this summer's report, this dotted line here, saying that there's a low likelihood but high impact storyline, including ice sheet instability under the top scenario, and that could lead to close to 2 meters. And then also what's new in this summer's report is it gives numbers, sorry, it's not readable, it's 2300 here. For 2300, for the lowest scenario, this is the same diagram you have just seen which stops in 2100. It's between 50 centimeters and 3 meters for the lowest scenario, the 2.6 at least, between 2 meters and 7 meters in 2300 for the 8.5 scenario. But again, with this comment here, which I think is sufficiently important to show it in big letters, but it's the same text as here, sea level rise greater than 15 meters in 2300 cannot be ruled out with high emissions. A very clear conclusion, once more, of this report is that every additional ton of CO2 or other greenhouse gas, but particularly CO2, moves us to the right in this diagram, showing the relationship between cumulative CO2 emissions and the warming. And another way to look at it, and this doesn't come from this summer's report, it comes from the IPCC special report on 1.5 degrees C warming published just 3 years ago in October 2018. The shape of global emissions for CO2 should be of this kind, with the famous net zero number. The zero here is, the zero line is here, crossed approximately around 2050, not for Europe, but for the world, which is not the same. When Europe says we're going to be neutral by 2050, well, maybe it's not so ambitious if you consider that it's the world which should be there. And then if you compare that with a picture which is not in the IPCC report, yes, I'll close in 1 minute, I'm almost over. If you compare to this diagram, this is the source, showing that if you look at the emissions over the last 150 years, you can fit an exponential on that curve. Of course, there are some fluctuations. It's an exponential with +1 + 65% per year. So we are clearly not moving in the right direction. If you look, and I know there's an update to this, but the update is not so different, and graphically this one is nicer. If you integrate the effect of all the NDCs in the framework of the Paris Agreement, you get here in 2025, here in 2030. So 2030 is still higher than 25. It's a little better than the business as usual scenario, but is so far from the trajectory that would allow respect of 1.5 degrees C warming. So we still have the choice. I'm convinced that there are many opportunities to integrate climate action in a broader context, and that there's a lot of value to do this in the framework of the Sustainable Development Goals, which of course include climate action, but also, as far as today's workshop is concerned, conservation of biodiversity, both in underwater and over land. Thank you very much for your attention.